Namaskar. I am Sandeep Chaudhari, working as Assistant Professor in Department of Electrical Engineering, All India Shri Shivaji Memorial Society's Institute of Information Technology, AISSMS, IOIT, Pune. This presentation is about moving iron instrument, construction and working. The presentation covers working principle of moving iron instrument, the types of moving iron instrument, construction of the two types of moving iron instruments, the advantages and disadvantages. Working principle of moving iron or MI instrument. It works on magnetic attraction or magnetic repulsion principle. In simple way, there is a magnetic coil and there is an iron piece which gets attracted towards the magnetic flux. So this is magnetic attraction. In case of repulsion, there are two magnetic pieces or iron pieces which repel each other, and a force is produced on the moving system. So these two principles of magnetic attraction and repulsion are utilized for the functioning of this moving iron instrument. The types: moving iron attraction type, it works on magnetic attraction principle, and moving iron repulsion type instrument, it works on magnetic repulsion principle. The constructional details of moving iron attraction type instrument are illustrated in this slide. This is a 3D sketch on the right hand side and a 2D sketch is drawn here on the left hand side. It consists of a coil which is wound on bobbin, and this bobbin center portion is hollow. One iron piece, oval shaped iron piece, is kept in the vicinity of this coil. This iron piece is supported on spindle. Spindle is a steel rod, and this iron piece is free to move like this. The moment this coil carries current, it develops a magnetic flux around it along the axis of the coil. This magnetic flux also links with the iron piece, and as per the laws of magnetism, this iron piece gets attracted towards the magnetic flux and it travels in this direction. The moment it happens, to the same spindle a pointer is attached. The pointer is deflected on a scale. So this is how the indication of instrument is obtained. So ultimately this iron piece gets attracted towards the magnetic flux produced by coil. Hence this instrument is called as moving iron attraction type instrument. The same thing is shown in the 2D sketch. For satisfactory working of any indicating instrument, three torques are essential. First one is deflecting torque, second one controlling torque, and third one damping torque. For moving iron instrument, the deflecting torque is obtained by the magnetic principles, magnetic attraction or repulsion. In this instrument, the deflecting torque is produced by magnetic attraction, as explained to you. Next is controlling torque. For controlling torque, gravity control mechanism is used. So a control weight is attached to this assembly, which consists of two rods arranged at right angles to each other. The control weight is attached at the end of this rod, and a balance weight is attached at the end of second rod. This balance weight is for mechanical balancing of the instrument. If this pointer is not showing you 0 when the instrument is not functioning, you have to adjust this balance weight so that the pointer rests to 0 when the instrument is not functioning. So this is for 0 adjustment in short. The control weight provides the controlling torque. As we know, this magnetic attraction causes the iron piece to move towards the coil. The moment the iron piece moves, this control weight also travels in this direction, and the gravity will try to pull it to its original position. So this is how the gravity acts, and the weight of the instrument acts along the gravity, and it produces controlling torque. So this is how controlling torque is obtained by means of control weight. Due to the deflecting torque and controlling torque, this moving system oscillates. So pointer will also oscillate, which is not desired. Hence, we need third torque known as damping torque. These oscillations produced by deflecting torque and controlling torque acting simultaneously should be absorbed. So the oscillations are absorbed by the damping mechanism. We have got an air cylinder here. The piston is arranged inside it. The rod is connected to the spindle. This chamber is closed from both sides. So whatever air is trapped inside this cylinder cannot come out. The moment this rod moves up and down, the piston movement in these two directions occurs. Suppose the spindle rotates due to the functioning of instrument, and this rod travels in upward direction. The moment this rod travels in upward direction, air pressure in this portion is more, and that pressurized air will try to push this piston in downward direction. In the similar way, when this rod travels in downward direction, piston will move in downward direction. The air pressure in this section will be more, and that air pressure will put a opposite force, or rather it will not allow the piston to move towards downward directions. So in all, the piston movement in upward or direct downward direction will be opposed by the air pressure, or it will absorb the upward downward movement of this rod, which is nothing but the oscillations. This is how the air friction damping is obtained. So this is about the deflecting torque, controlling torque, and damping torque in moving and attraction type instrument. Next type is moving and repulsion type instrument. Here, magnetic repulsion principle is utilized for the functioning of the instrument. Constructional details. It has got a coil made up of number of turns. Inside the coil, there is a small iron piece pasted along the periphery. We call it as fixed vane. There is a spindle, vertical part. To both sides of spindle, springs are attached. A pointer is attached to the spindle, and one more vane or one more iron piece is there, which is attached to the spindle by means of these connecting rods. So there are two iron pieces. One is a fixed iron piece or fixed vane, and another is a moving iron piece or moving vane mounted on the spindle. The moment this coil carries current, magnetic field is produced, and both iron pieces or vanes are magnetized with same polarity. Now, since the fixed vane and moving vane are present in same magnetic field, obviously the magnetic polarity on their faces will be similar. So like poles will face each other. So N pole of fixed vane and N pole of moving vane will face each other. In the similar way, S pole of fixed vane and S pole of moving vane will face each other. Hence there will be repulsion. The moment repulsive force acts, the moving member will move away and the deflection will be caused. The deflection is passed on to this vertical spindle, and the spindle rotates. The rotation is passed on to pointer, and pointer travels on this graduated scale. So this is in brief about construction and working of moving and repulsion type instrument. Now, deflecting torque is produced due to magnetic repulsion. Controlling torque will be provided by the springs, spirally wound springs. Damping torque arrangement is also there, which is not shown in the diagram, but air friction damping is there. Now, the symbol of moving an instrument is drawn in this way. You can observe it. This is a coil, zigzag, and one iron rod is shown, which is placed inside the coil, which resembles to the construction. So we got some iron piece or iron rod, which is surrounded by the coil. So this is about the symbolic representation of moving iron instrument. So we have seen moving iron attraction type and moving iron repulsion type instrument. The deflection of pointer theta is equal to I square by k into dm by d theta, where theta is the deflection of pointer in radian from zero position, I is the current passing through the coil, k the spring constant. The springs which are used for controlling torque, their constant is k, Newton meter per radian is the unit. dm by d theta is the rate of change of mutual inductance of the coil. The advantages of this instrument: this can be used for measuring AC as well as DC quantities. See, magnetic attraction or repulsion principle works well for both AC as well as DC. So this can work for AC as well as DC supply. Its torque to weight ratio is high because you can get a good strong magnetic field because of a coil which is a stationary member. So friction error will be reduced. The construction and the parts assembly work is easy. That's why these are cheaper than the other instruments. Cost is less. Reasonably accurate instruments. These are mechanically strong. So robustness of the instrument is better. This can operate in vertical or horizontal position. Disadvantages: the sensitivity of this instrument is lesser than the PMMC instrument because PMMC instrument has got a stronger operating magnetic field, and since the theta deflection of pointer is proportional to square of current, the scale is not uniform. It is cramped at the beginning. So while taking readings, it is a bit tedious. It's not simple because you have got a scale which is cramped at the beginning and which is not that way cramped at the end. So while taking reading, some more time is needed. Due to presence of external magnetic field, interference may be caused and instrument functioning may be disturbed. So the instrument accuracy is affected due to presence of stray magnetic field. And if you operate the instrument at different frequency, the response of the instrument is going to be different. The waveform error: you cannot use the same instrument for different waveforms like triangular, sinusoidal, square waveform, because for each shape of waveform you have to design the instrument separately, and it happens because of the non-linearity which is inherently there due to magnetic material BH curve property. Even though it can function for AC and DC, the scale for AC instrument and scale for DC instrument is different because 1 ampere AC and 1 ampere DC, they are going to produce different deflection. The theta will be different. So you have to calibrate the scale. So AC scale and DC scale will be different. The last point is extension of third point. The instrument readings are true for only the frequency for which it is designed. So 50 hertz sinusoidal wave, if the instrument is designed for that, and if you use it for 100 hertz frequency, it's going to respond in a different way and errors will be present. So for different frequencies, that is magnitude of frequency as well as nature of waveform, you have to design it differently. So this is about advantages and disadvantages of moving an instrument. Thank you. For more information, you can log on to www.aissmsiyt.org.